Alright. So in this video, we're going to talk about a specific case for um, thick-walled pressure vessels. Or sorry, thick-walled thick-walled pressure vessels. So we're talking about interference fits. Okay, so interference fits are when you have an internal element that is pressed into an outer element. Okay, so you add these two elements together to get a combined element. Okay, um, so these are used commonly. For example, something that's very common is for within furniture or in other mechanical systems, you use something like a dowel pin, where the pin is pressed into a hole on another piece. In rotating elements such as shafts, oftentimes shafts are press fit into a bearing housing or something like that. Um, but then, in non-cylindrical shapes, press fits are also used in things like your cell phone cases, for calculators, Tupperware containers, and like in rotary compressors. A lot of times, shafts are fit into bushings, I should say, um, here. All right. So, um, so if we press an inner element into an outer element, the outer element is going to exert a pressure, an external pressure on the inner element. Okay, we'll call that pressure P. All right, while the inner element will enact an equal and opposite pressure on the inside of the outer element. Okay, so we'll denote that with P. Okay, and then we're going to denote a couple of additional geometry things that we're going to talk about here. So the radius from the from the inside of the outer element to the inner radius of the outer element, we're going to denote that with a lowercase b o. The outer radius we're going to denote with a lowercase letter c. Okay. The inner radius of the inner element we're going to denote with a lowercase a. And then the outer radius of the inner element we're going to denote with a lowercase bi. Okay? Alright. So, so when we combine these two elements, that interface between the two is where our internal pressure is being applied to both sections. Okay, so 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 for our case of interference fits, we talked about you have to have the same pressure on the inner and outer element. Once we determine what that pressure is, we can then calculate what our radial stress and our tangential stress would be. So if you recall from earlier in the lecture, we had defined that our displacement in the radial direction is a function of the material properties and the radius and the tangential and radial stresses. Um, so, um, so what we can say here is that we can define the displacement of our outer element minus the displacement of our inner element, all right, would be equal to has to be equal to the difference between the internal radius and the external radius, and that's going to be equal to our displacement delta. Okay, so if you think about it, if the internal radius is larger, or the external radius of the inner element is larger than the outer element, we will have some interference. Okay, so this will be our interference term. Okay, so so if we look at equation 13, and for equation 13 we set the internal pressure equal to 0, and the external pressure equal to P. For the inner element, we plug in everything. So you plug in Ri is equal to A. You plug in Ro is equal to Bi. You plug all that in, we get our tangential stress. Okay, and we can do the same process for the outer element, where we would have Pi is equal to P, PO is equal to 0, and Ri would be equal to BO, and RO would be equal to BI. Okay, so since BI and BO are very similar, close to each other, okay, what we can then do is we can set BI equal to BO, and we're just going to set them all equal to the letter B. Alright, and we can take these two equations here, and we can simplify them down to these two equations. Alright, we know, so these are our two equations for our tangential stress within the inner and outer element. So this is the inner element's tangential stress, and this is the outer element's tangential stress. Okay, um, so we can then take for the boundary condition, we know that at the interface, the radial stress at the outer radius of the internal element and at the inner radius of the external element has to be equal to that combined pressure, which we'll denote as being equal to negative P. Alright, so if you plug in equations 21 and 22 into equation 17, so if we plug equation 21 and 23 into equation 17, so we're just plugging in our radial and our tangential stresses, we'll end up with this equation here. Alright, so this is for our strain, or sorry, our displacement at the inner or outer element. Okay, um, so that's for the, I guess I should say that's for the inner. This is for the inner element. Okay, alright, and then we can do the same thing for the outer element. Where you plug equations 22 and 23 into equation 17. Alright, and then the last part is we can plug in, we know that the displacement is equal to the difference between these displacements of the outer element and the inner element. Okay, so we can take that difference between the two, and we can plug them into, so we take equation 24 and equation 25, and we can then plug these in to equation, I believe, equation 5.8-18, and we can then solve for our delta term. All right, and then what we can then do is, now that we have delta, we can solve for the pressure. Okay, so we're going to rearrange that equation, and we can solve for the pressure at the internal surface, and this is the equation we end up getting. Okay, so once we have P, so we can then use P to find sigma r and sigma theta, all right, for the inner and outer cylinder. Okay. All right, so that concludes how you can determine the pressure due to an interference fit for an inner and outer cylinder, as long as you know the initial dimensions of the inner and outer cylinder, as well as the whatchamacallits, the the elastic properties, the elastic modulus, and the Poisson's ratio.